Good morning, everyone. I'm Andrea Porter with PG&E's Workforce Education and Training team. And today we have Brandon Gill and Jeff Stein with us, who will be presenting advanced concepts in designing and retrofitting energy efficient data centers. Okay, I'm going to hand off to Jeff and Brandon now. Thank you.
All right, so I'll go ahead and introduce myself. Jeff Stein. I've been at Taylor Engineers for 24 years now, and most of that time, or a good portion of that, I've been focused on data centers. So we are a consulting engineering firm. Most of our work is design for mechanical systems. A good portion of our work is also commissioning, both our own systems and designs from other engineers. We also do things like data center investigations, root cause analysis. We do a lot of peer review of other design, engineers design, energy studies for data centers, master planning. So I've been in the data center space pretty heavily for a lot of those 24 years. We also do a lot of work on codes and standards. So I've been the lead author for the data center requirements in both Title 24 and ASHRAE 90.1, and then in ASHRAE's data center standard 90.4. We do research on data centers. We've got some big contracts through like the California Energy Commission to do things like heat recovery and decarbonization in data center type spaces. We've been around this space for quite a bit.
Thanks, Jeff. Yeah, my name is Brandon Gill. I haven't been with Taylor quite as long as Jeff. I've been here for about 11 years. Been in the industry for about 16 and doing a variety of mechanical design, analysis, and commissioning. At this point, I've probably been the designer or the commissioning agent for on the order of 15 to 20 data centers at Rack Lab. In the past 4 or 5 years, I've been lucky enough to be involved with a number of liquid-cooled data center and rack lab projects. So we have a bunch of new material this year to share with you guys about what we've learned through being involved in those processes. I was a co-author on an ASHRAE data center controlled reliability article with Jeff a few years ago. I was lead author for a bunch of chilled water plant sequences that you now find in ASHRAE Guideline 36 that we often apply in data center context. And I also wrote the commissioning chapter you'll find in ASHRAE's Fundamentals of Design and Control of Chilled Water Plants course. We use a lot of those concepts when we are commissioning.
Here's our agenda for today. What is a data center? So for the new folks, this will be a good introduction. For the experienced folks, bear with us as we work our way through that. IT environmental requirements. Basically, how do you keep the computers happy in a data center? What requirements do they have, and how do you meet the requirements for things like temperature and humidity and so forth? There are basically two types of servers out there in the world, at least that we've worked with, which is air-cooled servers and liquid-cooled servers. And so we'll start with air-cooled, talk about how to come up with the basics of design, make sure that your design as an engineer is conveyed conceptually to the owner and to the other members of the team. What options do you have for air cooling? That's going to be a big part of our presentation over the next several hours. We'll switch then to liquid cooling, talk about the environmental requirements, if you will, for cooling liquid coolers and liquid cooled servers. What are the strategies? Then we'll go into design considerations, and these will be applicable both to air and liquid cooled. Design selections. How do you pick a design that's the most appropriate for your data center? And what are those options there? Control. How do you control your data center for maximum reliability and energy efficiency? And a lot of other important criteria. This is something we focus quite a bit on, and where we feel like success is made or lost for data centers for the large in very often. Commissioning, making sure that the design is followed through and that the systems work when first installed. Retrofit. We do a lot of work going into existing data centers to improve them both in terms of energy efficiency and reliability. We'll talk about some of our experiences there that might be applicable in your work. And lastly, we'll talk about data center heat recovery. Data centers consume a tremendous amount of power, which is converted to heat, which can be recovered and used to do useful work. Okay, what is a data center? And Brandon, you're going to need to help me out when we switch presenters to jump in. So there isn't a clear definition of a data center. It's not in the dictionary. We will define it as large group of network computers used by organizations for the remote processing of large amounts of data. Code here in California, Title 24 is the energy code. It doesn't actually have a data center definition. It uses computer room as the term. And it is any room within a building whose primary function is to house electronic equipment and has a power density exceeding 20 watts per square foot, which for those of you who have data center familiarity, that's not a very high density. Data centers today can easily be 200 watts per square foot or higher. So it's really almost any room dedicated to computer. ASHRAE uses pretty much the same definition. The new data center specific standard from ASHRAE has a minimum of 10 kW, but that's a pretty small number. So data centers can be anything from very small rooms to very large, basically dedicated to computers. Enterprise data centers, these are the Google, Apple, Microsoft type data centers, typically very large, 10 to 100. Now we're seeing 200, 300 megawatt enterprise data centers. Colocation data centers, which is basically like a data center hotel, if you will. Tenants can rent space in a data center, and those can also be pretty large. The ones we worked on are quite as large as the big enterprise, but 10 to 50 megawatts is not uncommon, even higher. And then you get into small sort of smaller type specialty spaces. We worked on rack labs where basically the computers themselves are sort of being experimented on and tested and it's a very different setting than these. And we're going to have some pictures and get into more details on all of these. Bench labs, IDF, MDF, telecom closets. So this might be just a small room in a big office building, maybe one on every floor. That's the telecom closet. That's considered a data center, at least by Title 24 in California. Edge computing is a growing area. And these are basically sort of smaller distributed versions of things like the enterprise data center, but can be really small, even less than 10 kW. And there are other types out there. Circling back through this list again, enterprise data centers have rows and rows of racks of computers, sort of like pizza boxes in a baker's rack. Typical rack will have 42U, which is the sort of height of definition of a computer. This is one of the old data centers we worked on a long time ago. Didn't have any type of containment. And it was an underfloor. This is a somewhat newer enterprise that has containment. We'll talk about what that means. And this is a very recent one that we're working on that's liquid cooled. All of these little tubes are liquid cooling to the computers in each of these racks. So one of the main sort of characteristics of an enterprise data center is that it's fairly neat and orderly. You can see it's sort of repetitious. Everything is clean. there's not a lot of people. Containment is definitely the standard of care for all data centers. It's required in California of this type. Here's a photo from one of the colos that we've worked in. They're often separated into cages for security and privacy reasons, not necessarily as well laid out and as orderly as the enterprise. Tenants are moving in and out. Containment is harder to control. You can see there's a person over here. Often tenants need to be in their spaces. So it's a little harder. Here's another photo from a colo where there's desks. Maybe people are working in spaces. This is a rack lab that we've worked on, and it's not nearly as clean. You can see there's all kinds of cabling going on, stretched across the room. There's lots of computers being moved in and moved out as they're tested and replaced, and lab experiments are being performed. People are moving in and out. Much harder to do things like containment. Even if you had containment walls and doors, you've got big gaps typically in your racks themselves between the gear. So much harder to do containment. And here's a bench lab, which is really just an office type space with lots and lots of computers in it. And so obviously there's no way to do containment. There's people walking around, and it just means basically an office with lots of IT loads. Edge computing. Edge computing is basically just where computing that is carried out at or near the source of the data. It can be indoor or outdoor type equipment. And the reason is the data sets are now so large that it makes more sense to process and store them locally rather than transport them to a regional cloud data center. And so we've worked on things like data center in a box, right? This is basically an air handler that's sort of the size of a shipping container, and the computer racks are inside the air handler. You can have a single rack data center. This has probably about 10 racks in it. You can even have just a simple pole mounted server platform. So this might be for something like cell service kind of data that has computers in it and needs cooling at that local level. And one of the real challenges with these types of edge computing is that it's harder to maintain the reliability that you can have in, say, a cloud type data center. For example, there's no vestibule. So on this product that we worked on, if you open the door, you can suck all kinds of dust and dirt and debris into your data center. And that's one of the big challenges with these types of edge computing facilities. But they're needed because the nature, the amount of data sort of forces it in that direction.
Next thing we're going to pivot to talk about a little bit is the anatomy of a data center. We'll start with looking over the anatomy of an example enterprise data center, and then we'll also look at the anatomy of a typical colo data center. So in an enterprise data center, you'll find a variety of room types. I think what most people think of as a data center are the data halls themselves, or what we call the white space where all the servers live. But around those servers in that white space, there's a whole bunch of additional infrastructure. One of those pieces of infrastructure is what we'll call a point of presence or a point of entry room. They do have slightly different technical meetings, but at a high level, and especially for us mechanical engineers, that's typically where all of the internet service providers are coming into the data center and interacting with the data center as well as with each other. The data centers also have very large electrical rooms to support things like transformers, switchgear, often unelectrical power supply systems. And then to support those uninterruptible power supplies, what you'll find in adjacent rooms, or sometimes the same room, is a bunch of batteries, right? And so these will often be in isolated rooms because the environmental requirements for the batteries are very different than the environmental requirements in the rest of the gear in the electrical room. And we'll talk about that in a little bit of detail, probably in Wednesday's class. Switchgear rooms, the distinction here between those and what I have above as an electrical room is essentially we're talking about medium voltage switchgear. You often see these in a separate room from the, say, 480 volt stuff that's going directly into the white space to serve the servers. There's almost always some sort of large mechanical room and often a mechanical yard as well. Generator rooms are required for backup power. So it's more often than not, it's a generator yard. If they're outdoor mounted, sometimes those generators will be mounted indoor and have external radiators. And then there's usually a support or admin space in an enterprise data center. So there'll be people who are often working there 24 hours a day. And so there will be a small or large admin office. And finally, you'll often see storage and testing areas. So these are where servers might be coming into the data center to start. And before they deploy them into the white space, they might have a dedicated burn-in or testing area within the data. Let's look at an example of that. So this is from a project that Jeff and I worked on years ago and has more or less all of these room types. So this particular data center had 4 large data halls, and those data halls were served by a mechanical yard that had flooded aisle air handlers. So these air handlers are just plugged into the side of the building, blasting cool air down the cold aisles in this data center. And we'll talk about the distinction between cold aisles and hot aisles in the later part of the class. Those air handlers were in turn supported by a mechanical yard that had a number of cooling towers and thermal energy storage tank or backup water tank. On the electrical side, you see that there are 2 electrical rooms feeding each of the data halls, and these ultimately have power that emanates out into the data halls, in this case by something called a Thorline busway, sort of an overhead form of electrical distribution to which you can plug in bus plugs that then serve the downstream servers. Each of those electrical rooms was supported by a battery room where the batteries for the UPSs lived, and so essentially, I kind of glossed over what a UPS is, or uninterruptible power supply, but the basic idea is that there's a brownout or a blackout in the data center and you need to transition over generator power, that UPS provides something to allow you to ride through before the generators kick on. And those batteries are what providing the power to the distribution before the generators start. On the far right of this example, we see that there's an admin space, so the offices, the point of presence rooms where the telecoms are coming into the building. And on the left, we have our rack storage and testing spaces for new racks coming in before deployment to the white space. And then finally, our 12 kV or medium voltage switchgear rooms on the left side of the building. The next example is for a colocation data center. Most of the parts and pieces are very similar. In this case, they're just arranged slightly different. Or in the previous example, we had a flooded aisle design. This colocation data center is laid out with underfloor distribution. So you don't, for instance, see a bunch of air handlers plugged into the side of the building. And you also see in this case that the electrical rooms are not staged immediately adjacent to the computer rooms. Instead, this engineer very likely used the underfloor as a means for distributing electrical out from the main electrical rooms to the computer rooms, where they're likely hitting power distribution units before going out to the servers. On the far right, in this case, you see we have another generator yard and some air-cooled chillers. There's an indoor mechanical room as well. Again, battery rooms and UPS room, that point of entry for where the telecoms are coming in, the NOC, and the operations center for the operators. So more or less the same things, just oriented in a slightly different way. This, I will hand it back over to Jeff to talk about environmental conditions for data centers.
Share my screen. Okay. Environmental conditions is basically, again, how to keep the computers themselves at temperature and so forth is required in a data center. So the first thing to talk about is where those environmental conditions are sort of measured and monitored. And it's all about the inlet temperature to the computers. Don't particularly care about what's coming out of the computers. And as I said, data centers are typically racks and racks of computers. The computers, when they're air cooled, will pull air in from the front side of the pizza box, if you will, and blow it out the back. And so you orient all the servers in what we call hot aisle, cold aisle. The fronts of the computers are all in one side, facing a row of racks that are also oriented to blow into the hot, right? Computers pull cold, air from what we call the cold aisle, blow it into the hot aisle. And the mechanical system has to deliver the cold air and then retrieve the hot air. And so what's the condition of the air entering the computers? ASHRAE has a technical committee called Technical Committee 9.9, and they put out a set of thermal guidelines that sort of is the de facto industry standard for those environmental conditions. And in this guideline, there are a set of criteria for things like dry bulb temperature, humidity, maximum dew point, maximum rate of change for different classes, if you will, of computers. There's what's called the recommended criteria, and then there's allowable for A1 class, A2, A3, and A4. And the recommended are the tightest in terms of things like the dry bulb and the humidity, and the allowable get wider and wider. So the recommended dry bulb is 64 to 80.6, but you're allowed to go down to 59 and up to 90 if you're an A1 versus an A2. You can go wider and wider and so forth. And I'm going to show this in a site chart in a second. But one thing that's sometimes often overlooked in this is things like the maximum rate of change. As the load changes, as the ambient outdoor conditions change, you could have swings in the temperatures and so forth in your data centers. And you don't want to be swinging too dramatically, according to this. And here's the range. You can swing 9 degrees per hour if you have tape storage, which almost nobody does anymore. That's a pretty antiquated technology at this point. And you can have much more sort of dramatic swings, if you will, 36 degrees in an hour for basically everything else. But then there's also a 9 limit in the shorter time scale. So here's basically the same information depicted on a psychrometric chart. We have the recommended envelope, and then the A1, A2, A3, and A4. And the recommended, you can see, has both a dry bulb minimum. This is in SI unit, minimum and a maximum, an RH maximum of 70%, right? In this case, but also a dew point maximum of 15 degrees, and then a dew point minimum. And it seems like a pretty wide envelope, but obviously if you're just designing and operating to a wider envelope, you have the potential for a much more energy efficient system, and your options for how to cool your data center and maintain humidity you have a much more wider array of options. So in our experience, there's quite a few large enterprise data centers that don't follow the ASHRAE guide. This is one that we've been working on or worked on that's in Alabama. And here's the ASHRAE envelope has changed over the years, it's gotten wider, but relative to what they're using in this data center, it's still pretty restrictive. This data center is only using an 80% maximum RH, doesn't have a maximum dew point. And what this allows them to do is to avoid any sort of mechanical cooling. All the cooling for this data center is done with an air economizer and direct evaporative cooling, which is pretty impressive in Alabama. Here's another client that we work with also is using only direct evap cooling at their data center in Phoenix, Arizona. They don't have any minimum humidity requirement, and their maximum humidity is also 80%. And comparing that to the ASHRAE envelope, they're also able to do all their cooling with air economizer and direct evap cooling, no mechanical cooling, even in Phoenix. So it really makes a big difference what envelope and what environmental criteria you're going to be designing and operating to. And so we're going to dig a little bit more into what's driving ASHRAE to these conditions. If you look at the servers themselves, they often will publish their criteria. And so this is from a HP server many years ago that said it can operate between 50 and 95, and that the humidity can be anywhere from 8% to 90%. And then they actually provided an option in this case for an ASHRAE class A3. Remember those classes? It had even wider dry bulb type range. And so, at least from our experience, what the computers are saying they can operate to is generally quite a bit wider than what the ASHRAE range is limited to. Now, there is a trade-off when you operate a computer at a higher temperature. It uses more power, and that's because the servers all have little fans on them to keep them cool, and those fans speed up as the temperature introduced to the server goes up. And this was some experiments we did many years ago at a data center where we sort of characterized that relationship between the temperature and the power. And it said we found on average 0.24% increase in the power consumption every degree you raise the temperature. We also found that every degree you raise the temperature, we could save more than this amount of power in our mechanical system. So it was always worthwhile on an energy basis. Other recent experiments we've run showed a smaller increase in power, and 2.3 decrease in server DT. Right. And so one of the other things that happens when the server fans speed up is that they need more air, right? So the delta T between what's going into the computer and coming out of it goes down as you provide warmer air to those computers. So not only using more power, but you need to feed it with more air. So there is a trade-off there as well. Again, it's a trade-off worth making, at least on a energy efficiency basis. A really big part of the discussion and decision is, what is the upper humidity limit going to be? As I showed you on those site charts, the clients we work with have only had an upper RH humidity requirement, not an upper dew point requirement. And there isn't a lot of data out there, but we have some anecdotal type data from our own experience. We've seen literally cases where the servers can start to rust. If you maintain a high enough relative humidity for long enough, the servers will start to rust. And we were supplying very cold air using an air economizer at 62 degrees, which meant that a lot of the time that air was being supplied at a relatively high RH. And that gave us this problem of rusting. We solved that problem pretty quickly by simply just raising the supplier set point, which effectively lowers the RH. We did an analysis of a data center that had been operating for years and basically came to a similar conclusion that if you're operating above 65%, even just 2% of the time, which is maybe 1,000 hours, that you can have an issue, but as long as you stay less than 2% of the time where you get above the 65, it wasn't an issue. So you can look at your sort of annual weather data and do the calculations pretty quickly and see how often you're going to be above 65%. There's no other evidence of high humidity risks that we've seen in terms of equipment failures or so forth. It's if others have information or data that they come across, please share it. The justification that the ASHRAE TC9.9 has for the dew point limit doesn't make any sense to me, at least. In their guideline, it says the maximum dew point limit helps reduce the risk of a corrosion-related failure by limiting the maximum RH. And of course, if your concern is RH, you don't necessarily need to control the dew point. You need to control the RH. They go on to say that the key change from the 2004 edition to all the later was the change from an RH limit to a dew point. The reason is to force operators to control moisture based on dew point and not RH, because dew point is fairly uniform throughout the data center, whereas RH is not. Again, this doesn't make any sense to me. If you're concerned about RH, control RH. Yes, it's not uniform, but it's easy to control it everywhere to whatever RH limit you want to set. And that's how we operate almost all the data centers we work with. We just have an RH maximum set point, and the system controls to that. And then lastly, from the guideline, it says another practical benefit of the change to a dew point from RH is that the operation within the will be sensible only, which doesn't make sense. It'll be sensible only whether it's RH or not. Also, having an RH limit greatly complicates control and operation and could require added humidification. Yeah, so I totally take issue with this. And again, going back to those side charts, if you have a maximum dew point limit, especially the ones within the guidelines, you're really limiting your option and increasing the cost of your equipment and of course the cost of operation. So we generally advise our clients to only use RH and not dew point as a max. Again, going back to that type of requirement, this is a data center where we did some analysis. This one happens to be in North Carolina, and the ASHRAE envelope is basically the shaded region, as I recall. And then, so the issue is above this dew point. If you only used an RH limit, the envelope would basically go up to here. And these hours of ambient conditions could be, again, met with direct evap cooling. But if you have to standard this limit here, now you're going to need DX cooling or chill water or some other much more expensive mechanical system and much less energy efficient. I think we sort of covered that one pretty thoroughly. Besides temperature and humidity, there are other environmental criteria that are of interest and concern in data centers. Well, actually, this is still on the humidity side. So where does the lower humidity limit come from? The ASHRAE lower humidity limit has sort of changed over the years. It used to be 20% or 30% lower humidity. Now it's 8%, but it also has a minimum dew point. And the concern with the lower end, the explanation has typically been electrostatic discharge. A person can generate electrostatic discharge with your finger when you touch something, for example. And so having a more humid, if it gets too dry, the electrostatic discharge that a person can generate goes up. You can have more of a discharge. But the reality is that the IT equipment is tested for electrostatic discharge resilience and is generally immune from electrostatic discharge. The problem is when you're handling the equipment. If you open up the component of a server, then you're at risk regardless of the humidity level. And so the recommended procedure is to use things like personnel grounding, cable grounding prior to plug-in, think wrist straps, grounded plates, grounded flooring, and other industries like the telecom industry. And there's also a group called the Electrostatic Discharge Association. They don't have any sort of humidity requirement. They're saying they actually used to have humidity, but have removed it as one of their criteria in the ESDA standard because it doesn't help. What helps are these sort of things. And their conclusion was basically there's no humidity level at which a CE rated server will be damaged by electrostatic discharge. And I'll talk about what a CE rated is. And there's no humidity level at which a non-rated component will not be damaged without grounding. So humidification to address ESD is a false sense of security. It's not going to protect your equipment if you're working on the components within a server. CE is the European Union's stamp, basically, that indicates the product has been assessed and deemed to meet the EU safety, health, and environmental requirements. And to achieve this rating, you need to basically subject the equipment to a certain external discharge. There's basically like a wand that's charged up and you touch the equipment and see if it gets fried. And so the equipment is sort of internally designed not to be damaged by electrostatic discharge. ASHRAE actually did some research on this subject a few years ago, and they said the testing that they did showed that that increasing humidity from 8% to 25% reduces the probability of generating a certain amount of charge from a person by 37%, but that adding ESD floors or shoes reduces the risk by basically 100%. And that even that 8 kV charge that person could generate was not a risk because the CE rated servers were able to withstand that level of charge anyway. We think again that the ASHRAE TC is doing a disservice by setting a humidity requirement that isn't justified by the research and the data that's out there. And one of the reasons why a lot of the clients we work with don't have a lower humidity requirement for their data center. So in addition to things like temperature and humidity, there are some other criteria I mentioned that need to be managed. One is particulates, cleanliness of the air, basically. There was a bunch of research that folks we know at Lawrence Berkeley Lab did that showed data centers with air economizers are not at higher risk than data centers without economizers. And so this was a big debate about, 10, 15 years ago when this research was done, is it safe to use air economizers in data centers, or are you at risk of damaging the equipment because of the dirty air? And the research they found was as long as you have filtration that's of the MERV 13 or higher, you're not at much risk. Now, we have worked in data centers that have had issues with particulates and basically dust, even though they had MERV 13, and that was because the data center wasn't kept at a positive pressure. And so not all the air getting into the space was actually going through the filters. There was air coming through exhaust air opening that didn't have any filters and settling on the equipment and causing failure. So it's important to keep the space positively pressurized. That data center also ended up installing particulate monitoring. So they were measuring not only the particulate levels in the space, but also in the outdoor air. And if it was a particularly low, poor air quality day, they actually would shut off their economizer to try to minimize their risk. So speaking of that kind of risk, one of the things that we certainly have to deal with here in California is wildfires. And what is the risk to a data center from wildfires if you are using outside air to cool your data center? So this slide shows the filtration efficiency at different particle sizes of different filter ratings, right? And so I said before, you should have at least a MERV 13. We're usually using even MERV 15. And wildfire smoke happens to be in this range, typically particle size. And you can see, for example, at a MERV 15, you've got an efficiency of 80 to 90%. And so most of the particulates, but not all, are going to get filtered out. The other question, of course, is, well, what does that mean? If you do have particles of this size, are they going to cause equipment failures? And I personally haven't seen any data on that. Like I said, there was we have some anecdotal data on the one data center that we worked with, but it was basically getting particles of every size because, again, it wasn't positively pressurized. Interesting to note that of the really, really small particles, the filtration efficiency goes back up. And I don't quite understand how this works, but this is scientific data. And then, of course, for very large size, the efficiency also gets much better. And so really the question is, in this range, and in this efficiency, is there risk to data centers? I'm not aware of any data showing that there is. We certainly worked on lots of data centers throughout California and elsewhere that use economizer only and have not, as far as I'm aware, experienced any sort of failures related to wildfires. So also, if you have a data center that has mechanical cooling, you can typically shut off an economizer, right? If your mechanical cooling is sized to meet your whole load, you can use particulate monitoring, or you can just use manual control, your nose, for the news report. If there's a risk, you can simply manually override. Another source of concern is gaseous contaminants. So these are not particulates, but gases in the air. And this is something that the ASHRAE TC has stressed in some of their guidelines. And I don't pretend to know a whole lot about exactly the chemistry of what's going on, but apparently the concern is with hydrogen sulfides, which can be produced by things like fossil fuel plants, wood pulping, sewage treatment, ore smelting, sulfuric acid manufacturing, landfills. The ASHRAE TC9.9 came out with a white paper, I guess now it's 15 years ago, that really sounded the alarm. The white paper said the recent increases in the rate of hardware failures in data centers led to the need for this white paper that recommends, in addition to temperature and humidity control, dust and gaseous contamination also monitored and controlled. And I did some research along with my friends at LBL and Berkeley, and went through all of the references in this emergency white paper, and we actually found out that there was no data cited in the paper that provided any information on cause and effects between contaminants and damage in data centers. The references really only highlighted some interest, and none of them actually even related to data centers. It was really a pretty misleading white paper, to say the least. The TC came out with a sort of backed off on that in their official guidelines that came out a couple years later and said, with a few localized and regional exceptions, outdoor air in North America and Europe is benign with respect to gaseous contaminant. Gas-based filtration is generally not required. Of course, particulate filtration is certainly required. The outdoor air quality in most major cities in South Asia and China is, however, very poor. So they said, okay, we're really just talking about South Asia and China. And they basically are still recommending that every data center, or at least ones that have this concern, have contaminant monitoring using copper and silver coupons. And they stipulate reactivity rates that would tell you if your reactivity rate is above this angstroms per month for copper or this angstroms per month for silver, that you have some risk and that you should be thinking about gas phase filtration. I am not aware of any data centers that actually have gas phase monitoring or filtration. I'm sure there are some out there. I can tell you again, anecdotally, we haven't seen any failures, aren't aware of any. I've worked in a data center that's literally across the street from a landfill for more than 10 years that uses airside economizing and direct evap cooling, and they have not indicated they've had any failures related to this. Yeah, so that's sort of where that stands. Okay, another important environmental criteria for computers is air velocity. Generally, you want to keep your cold aisles positive to your hot aisles, but it's also important not to be blowing air at a velocity that's too high. So here's a typical flooded aisle arrangement. You've got air handlers feeding into a supplied plenum and then air going from a plenum through a damper down the cold aisle. And the area of concern is the velocity as it enters this aisle. And what can happen is that if the velocity is too high, the Bernoulli effect, if you will, can create a zone of negative pressure in front of that server. It can basically sort of, the air rushing past it will suck air backwards through that server. And so the server won't be able to properly cool itself. Its fan won't be able to pull enough air from the cold aisle to keep it satisfied. And I've seen people use CFD, computational fluid dynamic modeling, to sort of validate data center designs that had things like 2,000 feet per minute velocity. And all I could say is that a CFD model can easily be garbage in, garbage out if you're not properly accounting for those sort of micro zones of negative pressure and the fan curves of the servers. We use a rule of thumb of 700 feet per minute, sometimes even 600 feet per minute. You don't want your air going faster than that down the aisle because you have this risk of starving servers. Yeah, so highest velocity at the cold aisle entrance where you need to be concerned. This is a graph showing what a server can handle in terms of external pressure. And if you put pressure on the server, it's going to flow more air than it was designed, right? At zero, you're no deviation in what the airflow is going to be. If you put more pressure on it by keeping your aisle positively pressurized, that's fine. Flowing more air through the server is not a problem. The problem is over here where again, the Bernoulli effect creates a negative pressure in front of the server. Then as the negative pressure gets more negative, if you will, you lose airflow. I don't know the history behind this data and what a prior generation 1U server is versus the current generation. I guess apparently newer servers are sort of more resilient to negative pressure. And so maybe that 600-700 feet per minute can get pushed up a little bit. But either way, you want to try not to keep the velocity from getting too high. Generally, servers are tested and designed with no external pressure. So they're not expecting to have any. You give them extra pressure, they'll work fine. You give them negative pressure, they start to have trouble. The fan speed algorithm will try and adjust to maintain temperatures within reliability specification. So the fan will speed up if it's getting less air, but at some point we'll run out of fan. All right, another BOD case study comparing direct.
Jeff, you have a bunch of hidden slides, so it skipped over all this stuff that I'm going to go through.
Okay.
Now it's probably a good time to take the 5-minute break you have the schedule before we jump into some HVAC cases, design items. I think.
Sounds good. I will set my timer for 5 minutes and I get back up in 5 minutes from right now.
All right, I've got 5 minutes, so I'm going to get rolling on the next section of the presentation. We're going to spend a little bit of time now talking about establishing basis of design conditions for a data center, and this very closely ties into the discussion of environmental conditions for servers that Jeff just went over in the preceding section. So we'll start with specifying appropriate design ambient environmental conditions for a data center. What do I mean by that? As many of you are probably familiar, if you're not designing for a data center, but say you're designing for an office building, you need to establish what the worst case ambient conditions are that you'll be designing to serve that facility under. So a typical design condition for a non-mission critical facility would be something that we call the ASHRAE 0.4% conditions. So on the cooling side, that would mean the ambient temperature, dry bulb temperature, and the coincident wet bulb that is exceeded for 0.4% of the year. And that makes sense for non-mission critical facilities because we're just dealing with human comfort most typically. And usually it's okay if temperature in a space drifts above, say, 74 degrees for a couple hours a year, because it just slightly impacts human comfort. And if we try to use more conservative conditions, there's a non-linear increase in the cost and size of the mechanical and electrical systems that need to support the space. For a data center, however, having exceedances 0.4% of the year could be particularly problematic, especially if those exceedances in turn lead to equipment failures or shutdowns that cause time out of service, which is very costly for a data center. So it's usually the case that for data centers, we use more conservative design conditions. And there are a whole bunch of options. Again, you could use the typical ASHRAE office building design conditions, but that's probably not a good idea. Another option would be to use the extreme dry bulb and wet bulb data that are also published by ASHRAE. But even that might be a little bit non-conservative because what is an extreme in one year may be exceeded in another year. So ASHRAE also publishes 5, 10, 20, and 50-year extreme dry bulb and wet bulb conditions for the climates for which or the climate zones for which you'll find data in the ASHRAE database. Some of those make a lot of sense, but they aren't the only options. A lot of times we've had owners request that we look at historical data and use that as a basis. So perhaps you have a site that does not map directly to any of the ASHRAE sites. And so you might be able to, on the other hand, find weather data from NOAA, so the federal government, that gives you historical data for a site, and you can mine those data to figure out what has actually occurred over the previous 15 years, and perhaps use that in conjunction with our best guess about what the world's going to be like with climate change to make an informed judgment for the owner. So let's start with a case study to show you what not to do. This was actually a colocation data center that I worked on in Silicon Valley about 7 years ago at this point. This particular facility was served by a water-cooled chilled water plant. So anytime you have a water-cooled chilled water plant, the design ambient wet bulb condition is particularly important because it drives the capacity of the cooling towers and whether the cooling towers can supply water, condenser water at a temperature that's sufficient for the water-cooled chiller. So a typical office building, the cooling towers in this climate would have been selected for an ambient wet bulb of 68.9 degrees Fahrenheit. What the engineer on this project elected to do, however, was use 67.5, which is even more aggressive than what you would likely use for an office building. So that was a bit of a head scratcher. What they should have considered, on the other hand, were some of the more extreme data that ASHRAE published. So we can see here, what this is telling us is that ASHRAE expects that over a typical 10-year period, the highest ambient wet bulb will be 75 degrees Fahrenheit. Over a 20-year, it might get up to 76.5. And then over a 50-year, they're expecting up to 78.3. So what was the ultimate impact of this error on the part of the engineer? Well, during the summer of 2017, we had an extended heat wave that was not only warm, but it was also humid. So there were 6 consecutive days where the ambient wet bulb exceeded the design condition for this data center. And the worst of those days you can see was 6/18, which I think was a Saturday. And that weekend we got a call from the owner, hey, we've been having issues with our chilled water plant with chillers tripping all weekend. What can you do to help us? So by Monday we were contracted to help them figure out what was going on and how to resolve the issue. You can see on that day with the highest ambient wet bulb, this was essentially the sequence of events that they experienced. By 9 a.m., the wet bulb had already gotten high enough that it exceeded the design condition, and they had their first chiller surge fault. So essentially the chiller was operating at too high lift for the concurrent load condition. It couldn't handle it, and it tripped on a surge fault. So they had to manually restart the chiller. We then see by 2 in the afternoon, obviously the ambient wet bulb just kept getting higher and higher, which is what this red line is showing throughout the day. And by 2, they just started having repeated trips on surge conditions across all 4 chillers, as well as overcurrent faults, which is another condition that can occur as a result of surge. And so we basically had operators playing whack-a-mole to keep the chillers online and prevent this colocation data center from going offline. So this can show you more or less, it's here to demonstrate what can go wrong if you don't consider or choose the right design ambient conditions for your data set. So again, going back to the statement I made earlier, there's no one right answer for that facility other than obviously the one that they picked. And when you're coming up with recommended design environmental conditions for a given facility, there are 3 factors you need to weigh. One is first cost implications. Second is energy impact. And the third is the risk associated with exceedances of those design conditions. So the more conservative or the higher you make your design conditions, the higher the first cost is going to be, because it will drive the size of your mechanical equipment up, as well as the electrical infrastructure that's supporting that equipment. There can be energy costs, ongoing energy impact as well. Sometimes oversizing is a good thing. As an example, if you oversize cooling towers for that once in a 50-year event, well, it's going to be the case that the cooling tower fans are going to have to work less hard during most conditions in order to meet the target conditions. So there can be a first cost hit, perhaps a long-term energy efficiency benefit of some oversize. On the other end, a lot of oversizing can be problematic from an operational scenario. And finally, probably the most important thing from an owner's perspective is that you're not trying to save them so much on first cost that you introduce risk associated with exceeding those design conditions, like we just saw in this previous example. So stepping inside the facility, we just kind of touched on some considerations for the design aiming conditions, but we also need to consider the design cold aisle temperature and our conditions. As Jeff talked about earlier, the most important thing is the temperatures entering the pizza box, not necessarily the temperatures leaving the pizza box, because they internally have fans, at least for an air-cooled server, that are dynamically modulating speed in order to make sure that chip temperatures are staying where the manufacturer wants them. So what are the appropriate conditions for cold aisles? They're highly customer dependent. What we generally find is that colocation facilities want tighter environmental conditions than enterprise data centers. And this is simply because they have multiple customers within the data center and they're trying to cater to the needs of the most conservative customer in many cases. That in turn drives them to using more conservative conditions broadly across the data center, because it's not like you can have a server cage in one part of the data center that, particularly for using something like an underfloor distribution, that's controlled to one set of conditions, and another part of the data center in that same data hall that's controlled to a different set of conditions. One interesting thing that you'll find is that in contrast to there being just a fixed environmental condition within the cold aisle, owners might have a frequency dependent requirement. They might say, for instance, that, look, we need it to be between 60 and 90 degrees Fahrenheit 100% of the year, but we will allow those requirements to be relaxed during extreme conditions. So during, say, really, really hot days, it's okay if, for that 0.01% of the year, it does get up to 90, but for the rest of the year, we need it to be below 80, right? So they're becoming more strict for I guess, smaller periods of time. Another consideration is the design airside delta T of servers, of the air handling equipment that's serving servers. So you might think that if you know the servers that are going into your facility have an airside delta T, meaning that the difference between temperature going in and the temperature leaving of, say, 20 degrees at your entering server temperature, then that's what you should be selecting your air handlers for. But in reality, the air handlers typically need to be selected for something that's a little bit more conservative than the servers for a couple of reasons. The first is leakage across containment. So usually in enterprise facilities, we have, as Jeff was talking about earlier, some level of containment isolating the cold aisles from the hot aisles. Well, that containment is imperfect. So we have some air that, instead of going through the servers, is bleeding through the containment, which in turn lowers the delta T that the air handling equipment sees. We also have a small amount of heat transfer through the containment itself, right? That's usually a small factor, but it also contributes to reducing the airside delta T. And so in this example, if, for instance, we had a 20-degree delta T at servers, which is pretty low for modern equipment, maybe we should be designing our air handlers for 17 or 18 degrees. Most facilities these days, we're designing for between 20 and 25 on the air handler side. And that's simply because most servers will be higher than that. They'll be on the order of 30 degrees at delta T at design conditions. But it doesn't necessarily make sense for most facilities to design based on the products that we're seeing today. It could very well be that the data center sees a large change over 10 years in the type of equipment that used in that data center, and therefore our airside selections need to be flexible enough to accommodate changing IT equipment within the data hall. All right, this is also something Jeff talked about a little bit earlier, which is that as the inlet temperature going into the servers rises, what we see is a decrease in the IT delta T. And so think about it this way. We have a server that has a fan inside of it. That fan is being controlled to maintain physical chip temperatures. And obviously, as we send warmer air into the server, the amount of air that's needed to maintain those chip temperatures tends to rise. So that internal server fan speeds up using a PID loop or some other fuzzy logic algorithm that the server manufacturer has programmed. So we see this reduction in delta T as we raise our entering dry bulb temperature to the servers, and that in turn has an impact on how we design our air cycle, right? It's essentially about the higher the entering air temperature that we design for, often that means the lower delta T and therefore bigger air handling. One important thing to note is that from an efficiency perspective, there can be a significant benefit there. We have an airside economizer, for instance. the higher we allow the entering temperature to be, the more economizer hours that we'll get out of the system. Okay, looking at the supply air temperature to the server. So you might think, for instance, that if I'm trying to maintain, as an example, a server entering air temperature of, I don't know, 78 degrees. Well, to do that, then my air handling equipment needs to supply air at 78 degrees. But that doesn't account for the fact that there can be some recirculation from the hot aisle to the cold aisle. And there can also just be some thermal pickup across surfaces that are warmer, which can cause some degradation at supply air temperature. So usually what we'll do is select a supply air temperature that's on the order of 2 to 3 degrees less than the temperature that we're trying to maintain within the cold aisle. So again, if I'm trying to maintain 78 in the cold aisle, then I might be designing for 75 degree supply air. Design supply air temperature in turn impacts the design requirements for the chilled water supply temperature that I'm supplying to those air handler coils. So if we're looking at a chilled water plant, we're controlling a chilled water supply temperature. If we're looking at what we'll call a condenser water plant that serves closed condenser water to air handlers, then we're targeting a designed condenser water supply temperature. One common mistake that was made many years ago, we see it less frequently now, was that designers would design their chilled water plants for 42 or 44 degrees Fahrenheit at chilled water supply the same way they would for a chilled water plant serving an office building. But in an office building, you're trying to make air that's between 55 and 65 degrees. As we just talked about in the preceding example, I might be trying to make 75 degree air. So if I'm trying to make 75 degree air, I don't really need 42 degree water to do that. I can effectively make 75 degree air with 60 degree water, maybe even 65 degree water. And the warmer I make my chilled water supply temperature, the more efficient those chillers are going to operate. And if it's a data center where I have a waterside economizer, the more waterside economizer hours I'll get as well. One note here, and we'll talk about this a bit more when we get to the liquid cooled server portion of this class, is that it might make sense to use separate distribution loops for the liquid cooled servers and the air cooled servers, or the systems that are serving those air cooled servers, because liquid cooled servers can operate at much higher temperatures or much higher water supply temperatures than even the air cooled server systems can. So it might be supplying 60 degree water to an air handler that's serving air cooled air cooled servers. I could, on the other hand, serve up to, say, 90 degree Fahrenheit water to liquid cooled servers. So that changes the optimal plant scheme. All right. And this next one, I think, Jeff, you're going to cover. So I'll hand this back over to you.
Okay. Yeah. Share. Okay. This was a really interesting exercise we went through with one of our clients designing a data center in North Carolina. And they had a lot of data on the equipment that was going to go into the data center in terms of the delta T across that equipment based on the inlet temperature. And I can't share all the details on the equipment, but this red heavier line is the weighted average for all of the equipment that was going to go into the data center. So you can see if we were to supply 77 degree or lower temperature, the average delta T across the equipment was 28 degrees. And then if we supplied warmer temperature, say 91 degrees, then the average delta T across that equipment was going to be less than 20 degrees. And we went through this exercise to sort of optimize the design based on the fact that we'd need more air if we were going to design it around a higher temperature, or less air if we were going to design it around a lower temperature. There's a lot going on here. Let me try to unpack it quickly. This is a bin plot of all the hours in climate. We were looking at things like direct DX cooling, basically packaged rooftop units with DX, and airside economizing was one of the options. And so if we used, say, a 75 degree supplier, we would need a 25 degree delta T at the air handler. And we would need 100% DX cooling capacity because our return air would be below our extreme ambient dry bulb. If we raised it all the way up to a 93 degree supplier temperature, we'd have a low delta T, 15 degrees, but we could actually get away with partial DX. In this case, I think it was 81%. So we could cut out 21% of our DX capacity because our return air temperature was actually going to be above the worst case ambient temperature. So we would always be on economizer, even on the 50-year extreme hottest day. And then we also looked at direct cooling, and we found that the worst case condition, which would be our extreme wet bulb temperature, which was, I guess, around 81 degrees, we would be supplying 87 degrees into the space, which would mean an 18 degree delta T that we would need to size our fans for. And so it just shows you how the level of detail you can get to in terms of sizing the CFM of your air handling based on what supplier temperature you're going to design for. I think in the end, they decided to be conservative and design it for a 75 degree supplier temperature. So they had 100% cooling DX capacity. But then I think the plan was to operate it at a higher temperature as available to reduce the amount of DX and increase the amount of air economizing that they were going to be able to operate at. I think we're going back to you, Brandon.
Nope, I think you're gone for a while.
Okay, sorry. Okay, so we talked about what the computers need to stay happy. We've talked about what ambient conditions you want to design for. What are some of the designs that you can use? And we've alluded to this on some of the past slides. Now we're going to dig into it in a little bit more detail. Focusing on air cooling mostly today and liquid cooling a little bit more this afternoon or on Wednesday. Air cooling. First, we're going to talk about containment. We've alluded to this a little bit. We want to really explain the concept and the practice because it's critical or make a huge difference for air cooling. Then we'll get into technologies, right? Crack unit, computer room air conditioning, CRAC. There's different flavors of that now. We'll talk about packaged and custom DX units, basically rooftop air conditioning unit, direct evap cooling. We talked about it a little bit. We're going to dig into that in more detail. Indirect evap cooling, a couple sort of niche specialty types of cooling systems. Then we'll get into central plants with chilled water, with water or air side economizers, modularized data centers, distributed cooling, where air handlers are much closer to your computers, using either in-row coolers or rear doors. And then we'll get into true liquid cooling using cold plates or immersion cooling. Okay, so containment. We showed this before. You want your computers set up in cold aisles. The next step, and then that hot and cold aisle, the sort of original computer rooms or data centers were typically raised floor where the air was coming out of the floor in the cold aisles. And originally data centers didn't have containment. It just wasn't and what would happen is that you would have hot spots at the top of the racks. Typically the servers at the bottom of the rack were usually okay because they were getting very close, sort of coupled air right out of the floor, but the space was largely mixed up, and the servers often, instead of pulling the cold air coming out of the floor, they were pulling air from the hot aisles back into the servers. And so there was common to have hot spots and failures. you needed to blow a lot of air. The supply from the HVAC needed to be much, much greater than the airflow that the servers were pulling. Cold supply air, not uncommon in early generations for data centers to be supplying in the 50, 55 degree supply air temperature, and basically sort of keeping the whole space almost like a meat locker. The original crack units were designed for operated typically at a 70 to 73 degree return temperature, which the whole space was much colder. Containment is basically sort of ducting the air through the servers, right? And so one way to do that is with cold aisle containment. And so if you sort of block off, duct the air on the supply side, you can basically ensure that you're getting only cold air through the servers. You'll have less hot spots, less failures. Now the supply air from your air handling system can be roughly the same as the supply volume through your servers. You can supply at a warmer temperature. You can return at a hotter temperature. Gives you lots of improvement options for energy efficiency right there. So here's the more modern incarnation of a lot of the air cooling is this flooded aisle concept where you're just supplying air into the space, which effectively makes the whole space a cold aisle. The hot aisles are contained with doors and walls so that the only air path is basically from the cold aisle through the servers back into the hot aisles. What this isn't showing is that there's usually a ceiling. The hot aisles are connected to the ceiling, and then the ceiling is then returned back to the air handlers. Options for controlling common supply fan speed. So typically these would be air handlers pressurizing the space. And the most common way to control the speed or the flow of air from the air handlers is by measuring the differential pressure between the cold aisles and the servers are pulling air. So if the servers are pulling more air than is being supplied, they will basically suck the cold aisles negative, pressurize the hot aisle, which means you aren't supplying enough air. If you speed up the supply fans so that they're supplying more air than the servers are pulling, then the cold aisle will become positively pressurized relative to the hot aisle. And that will ensure that you have cold air all the way down your aisle, that the servers aren't sucking backwards through cracks or through empty spaces in the containment. That actually, if there are cracks or gaps in the containment, and there always are, this positively pressurized air in the cold aisle will just push through those gaps into the hot aisle. So that's the most common way. We've also seen designs that use DP in combination or only using cold aisle temperature. Again, if you're measuring all your temperature with an array of sensors suspended in the cold aisles, that sort of ensures that you're getting cold air into the servers at the far end of the room. And so even if you aren't controlling to it, it's very common to at least measure that as a way to validate that the air going into those servers is the right temperature. And we haven't had much success with this, but we've been trying for many years to try to get feedback on the data from the computers to the mechanical system. You would think that's not such a difficult thing, but the computers are not on the same sort of network, if you will. And so transferring data on what kind of temperatures and flow rates, and there's a lot of sensors on each server. There's a lot of data available, but it's not been easily communicated between that IT and the mechanical system. But if you had that data, then you wouldn't necessarily need, for example, any of your own sensors in the cold aisle, because every server could tell you what temperature at least was coming out of it. And that could be used as a way to adjust your fan speed, your supplier temperatures, and so forth. So curious if other folks have had success with that. And unfortunately, we have not on most of our projects. Other forms of containment. This is another form using in-row coolers. So an in-row cooler is basically a fan coil that sits between the racks. You can see computer rack, in-row cooler. And so the computer racks are pulling air from cold, blowing it into hot. The in-row coolers work in the opposite direction. They pull air from the hot aisle and blow it into the cold. So you can basically put a lid and doors on the hot aisle and use your in-row cooler. And it's a form of what we call close coupled cooling. You're putting your cooling very, very close to your racks. So there isn't a lot of pressure drop to your ductwork because there is no ductwork. Big downside of this, of course, is that it doesn't have an air economizer. So it's relying 100% on chilled water or whatever fluid you're bringing to your cooler, in-row cooler. Another form of containment is a chimney rack. So instead of using walls and doors to block off your hot aisle or your cold aisle, you can simply have a rack that's a little bit deeper than a standard rack. And the back of the rack is basically sort of a return duct that can then just be ducted up into your ceiling, right? And so there's no way for the air to go out of the rack and back into the front of another rack or server. It's all being collected and basically ducted to your ceiling, which goes back to your area. Containment has been required in Title 24 since 2013, so more than 10 years now. Hot aisle in general is better because it keeps more of your space at a more reasonable temperature for human beings, but sometimes cold aisle is the only option. If you're retrofitting an existing raised floor data center, that's almost always the only option that's going to be available. Containment, again, reduces hotspots, increases capacity. We've had data centers that simply haven't been able to put in the servers because they've run out of air, if you will. Without containment, you need to blow a lot more air than your servers are pulling. And so they often run out of airflow capacity before they run out of electrical capacity. Saves fan, pump, compressor energy, heat recovery. We'll talk about that on Wednesday. But when you have containment, as I said, you can run at higher supply temperatures and return temperatures, which opens up all kinds of opportunities for heat recovery. There are some challenges, integration with fire protection, lighting, and telecom. So if you're adding walls and lids and things to your data center, you need to make sure that your fire sprinkler system has the proper coverage. If it's a retrofit, this often means adding a sprinkler head. Your light fixtures, if it's a retrofit, you may need to add new lights because you're adding walls basically. And when you do have containment, hot aisles can get pretty hot. So there's issues with people. It doesn't bother the computers to have hot aisles, but it can bother people working in them. You need to think about how you're going to control your airflow, and it actually can introduce some risks because now because you've sort of separated things out, that there's a possibility that some hot aisles or cold aisles won't get the airflow that they need. So it needs to be planned out. Air-cooled rack cooling option. So you'll recognize or may recall this photo from way back when. This was very early generation data center, no containment. These are crack units. So they're DX air conditioners, basically. And on the roof of that facility was basically just a sea of condensing units for each one of these crack units. The ones in that data center and in almost all data centers 20 years ago were constant speed. They used house fans, belt drives. They usually had steam humidifiers and electric resistance reheat. And the humidifiers and reheat was to be able to maintain very tight humidity conditions. One thing we found with data centers like that is that the humidity sensors that the crack units were using would drift out of calibration. And so it would be very common for one crack unit to be humidifying and the one right next to it to be dehumidifying with the electric resistance reheat. Very inefficient and basically constant speed fan. If you know the term PUE, PUE stands for power utilization effectiveness. And it's basically the total power consumed in a data center divided by the IT power. And that meant basically how much power was consumed by your mechanical and your electrical equipment versus by your computers. Very common to have a PUE of 1.5 or 2 or even 3, meaning that the air conditioning unit was using as much or even sometimes twice as much energy as the computers. By comparison, a good PUE today is like 1.1, which means the mechanical system is only using about 10% of the power of your computer. We've come a long way. And even with crack units, we've come a long way. You can now get crack units with plenum fans instead of housed fans. The fans are more efficient. You don't have belts to deal with. EC stands for electrically commutated motors, like a variable speed drive. So now you can save fan energy, various speeds. You can get ultrasonic humidifiers, which are basically adiabatic. They're not adding heat to the system like a steam humidifier would. You can get refrigerant economizers. We'll talk about that in a second. You can tie them into an air side economizer so you can get some free cooling. And so crack units are still used in a lot of data centers. One of the main advantages, especially originally, was they were very simple and reliable. Basically, each one was sort of standalone. You didn't to coordinate operation between them, among them. So those sort of central managing function don't have water, don't have to deal with freeze protection like you would, for example, in a cooling tower system. Big disadvantage, of course, is efficiency. I talked about PUE, not very efficient. And first cost. One of the big drivers of first cost in a data center is the peak power. And so if you're using something that's like an air-cooled DX system, it has a very high peak power because it has to be able to meet the load and the highest ambient temperature you're designing for. And that means not only do you need to size the electrical service to the facility based on that, but you're typically also sizing your generator based on that. If you've got a peak PUE of 1.5, for example, that means you need to have 50% more generator capacity than just the capacity needed by your computer. Pumped refrigerant economizer. So modern crack units, some of them have this ability to do some economizing in terms of bypassing the compressor. So this particular manufacturer's model has the option of using either a compressor or just simply a refrigerant pump. So it's not going through the vapor compression cycle that a compressor does in an air conditioner, basically using the refrigerant like a simple heat transfer fluid. And this particular design, you have 2 compressors and 2 pumps, and you can switch basically half your capacity from compressor to pump or all your capacity. So it makes it a partially integrated economizer, which means the system needs to sort of guess if the ambient is going to be able to meet the load, or at least half the load, when you switch from compressor to pump, which means that the controls need to be pretty conservative and you don't get the full sort of economizing potential out of it. We'll talk about this more when we get into waterside economizers. I would say a more evolved and efficient design is this one from another manufacturer that has the DX condenser in series with this passive condenser. And so it's not necessarily an either or. It actually allows you to sort of gradually shift cooling from the DX to the economizer system. And so we would call this a fully integrated economizer. And this one, we haven't used it ourselves on projects, but we've evaluated it for other projects. And it's a pretty clever design in that it can be pretty efficient with air delivered at 75 degrees and 20-degree delta T. This system can be doing 100% free cooling at 65 ambient. And in a lot of climates, that's most of the year. It's a pretty interesting design for making your crack units more energy efficient. This is a data center we've worked on for a few years. Wasn't our design originally, but we've done a lot of troubleshooting and upgrades to it. It's using packaged rooftop units, DX boxcar units that you might see in an office. But as you can see, basically the roof is packed with them to meet the high loads in this data center. And this one has both ASC airside economizing and DEC direct evap cooling. And so it has mechanical cooling, but also has free cooling with outside air and what I would argue is free cooling using direct evap. So it's a very efficient system for much of the year. Almost never need mechanical cooling. So yeah, what is the advantage of this system? It can extend the hours of free cooling with the evap cooler. Almost no mechanical cooling required. Evap cooling provides humidification, basically sort of as a freebie, if that's important. But we've argued that it isn't important, but a lot of data centers still insist on it. It gives you some added reliability. Not only, you basically have sort of three sources of cooling. You've got mechanical cooling, economizer cooling, and evaporative cooling. The disadvantages, you're adding some cost by having those three sources. It can get complicated trying to stage the different option spatial requirements. As you saw, that roof was pretty much maxed out. This was a multi-story data center, and it was serving 2 floors. That's pretty much the limit, depending on your sort of watts per square foot that you can get with a rooftop air economizer system. Higher RH and data center. If you're using direct evap, you are operating at a higher relative humidity. As we talked about earlier, you can still stay within an 80% maximum, or even a more restrictive one just by limiting how much evap cooling you're doing. In practice, we came across a bunch of operational issues in this data center and similar one with this kind of a concept. The box cars, which are packaged products used on hundreds, thousands of buildings of different types, they don't always work very smoothly. These ones had 4 compressor stages that resulted in pretty significant cycling and fire temperature swings. To make it even worse, the internal sequences that came with the units didn't make a whole lot of sense, which resulted in even more cycling and swinging. They had long minimum runtime, so the compressor would come on, overcool it, would keep running and overcooling even more, and then it would have a long minimum off time. So then this temperature would get higher. Did weird things with rotating compressors, turning on too many compressors. And so what was happening is that DX was fighting both with the economizer and with the evaporative cooling. And so in the end, it became almost impossible. Well, it became very difficult to control the units, and they had to sort of make it somewhat of a non-integrated system between the three. There were also significant issues with exhaust reentrainment. Those packaged boxcars only come sort of in one flavor in terms of where the outside air comes in and where the exhaust goes out. And it was very hard to arrange them so that one wasn't blowing hot air into another. So there's some practical issues there. Okay. Similar to that other roof shot we showed, these are rooftop units that have air economizing and direct evap, but they're custom units. One of the big advantages there is the ability to sort of configure the intake and exhaust to try to minimize reentrainment. So in this case, the exhaust is basically sort of shot up in the air to try to keep it away from these intakes on the side. And we had some more flexibility on control sequences to deal with some of the goofy stuff we were seeing on compressor staging and minimum runtime. So it had a lot of the advantages of efficiency and redundancy, and sort of address some of those disadvantages. All right. Another type of system is a built up DX with an air economizer. So similar to package DX, this is building basically a huge mechanical room that has banks of cooling coils, banks of supply fans. Maybe I'll go to the next section. So here's a section view through that data center. And here's this built up system, this huge 20-foot high set of cooling coils served by double height bank of supply fans, outside air one side. So one of the nice things about this is now we've set up the whole data center so that all the outside air comes in one side, all the exhaust air goes out the other side. So far away, blowing away. So this really is one of the better ways to deal with that exhaust reentrainment, right? There was no exhaust reentrainment to speak of coming all the way around and back in this side. So, a very efficient design because it's got an air economizer, right? We've got our outside air, return air, got our exhaust relief system, no water, right? Air cooled. Has still relatively high peak PUE because we're air cooling DX, but generally very efficient because of the air economizer. Here's a data center that's using direct evap only. This one I think was in Nevada. It's sort of a built up system. So we've got these air handlers, sort of like a fan wall set up. This is a plan view. So we've got outside air coming through filters. The return air isn't shown here. There's dampers above coming down from the ceiling plenum. So we've got outside air, return air going through these plenum fans. And then here's a section through the fans, push through evaporative media. And then there's a bypass. I'm going to ask folks if you could just shout out, why would you need a bypass damper around your evaporative media? Can anyone tell? You guys have the ability to talk. So if you have any idea why, let me know. Even if it's a guess, take a guess. Nobody's willing to hazard a guess. Okay, so the main reason to have a bypass is somebody going to try? Mohammed, are you trying to speak?
I guess it's a freeze protection.
Freeze protection. That is the good answer. I'm going to say it's not the right answer. The freeze protection would come primarily from your economizer dampers, right? Your outside air and your return damper, even if it's 0 degrees outside, you're going to be blending outside air and return air. So you're mostly going to be returning air and blending it with outside air. And so if you were going to do, say, evaporating water to raise your humidity in the winter, you're sort of protected by your economizer mixing. If you don't care about low humidity, then you would never run your evap when it's cold out. You would just be on a pure economizer. But thank you for hazarding a guess. Anyone else want to hazard a guess? So the two main reasons are temperature control. Evap media is not easy to control. It's sort of an on-off thing. And we'll get into that detail more, but let's just say that this is a single stage of evap media. If you turn it on and cooled all of your air, it would overcool and potentially over humidify. And so basically blend air that's overcooled with air that's undercooled to get combined combination that's at the right temperature and humidity for your supplier. In this case, this design had what I would argue is somewhat of a fatal flaw. The other reason to have a bypass is for energy efficiency, right? If you're most of the time in the data center, you're with an air economizer, you're going to be at 100% economizer cooling or mixing, and you won't need any direct evap. And so in those periods, you had a bypass here, you save the pressure drop in this media, but that's not the main reason. The main reason is the temperature control. This data center had a fatal flaw in that the bypass was right under the evap media right before it went into the data center. And so the air didn't mix. What's happening is we would have sort of a band of hot air coming out at the low elevation with a band of cold air at the higher elevation. And so the servers that were on the bottom of the racks were seeing hot air. The servers at the top of the racks are seeing cold air. And that's not acceptable. You need to basically have the environmental criteria met for all the servers. So I won't get into how we solved this problem, but we ended up coming up with a fix. So evap media is basically corrugated cardboard that you're dripping water over it so that dry air going into it comes out as cold and moisture air coming out of it. And that temperature and humidity can be controlled by bypassing. We'll talk about a couple other options. One other nice feature of direct evap is that it provides an extra level of filtration. It's basically an air washer. And so not only is it cooling the air, but it's taking out some of the particulates and aerosols and things that may not have been caught by your filter. You're still going to have an outside air filter upstream of this, but you get an extra level of filtration with this air washer. And psychrometrically, this is what direct evap looks like. Here's if your ambient temperature, for example, is 105 degrees in Phoenix and happens to be at 11% RH at this point here, running it through that media can dry it, can cool it down to 74 degrees, for example, and potentially even lower depending on the effectiveness of your media. But this was the design temperature. So you would only take it down as low as you needed. And then as it goes through your data center, it gets heated up and returned back from your house at some higher temperature. Some more characteristics about the media. It comes in different thicknesses. And as the thickness, as it gets thicker, as you can imagine, the effectiveness improves. And the effectiveness is basically how far from whatever condition you start at, how close can you get to this saturation line? 80% effectiveness means you can get 80% of the way from here to there. And that may be more than you need, but there may be cases where you need that level of effectiveness. And so if you need more effectiveness, you can increase the thickness of the media. There's a diminishing return. The effectiveness is not linear with the depth. So for example, 12-inch media over here is only 20% more effective than say 6-inch, right? You might go from 70% to 90% at a velocity of 500 feet. But the pressure drop of the media does go up linearly. And so a 12-inch media is 200% of the pressure drop of a 6-inch media. And so you want to think carefully and run your sort of design condition calculations to figure out, well, what's the thinnest media I can get away with. In almost all the cases we've worked on, 6 inches is sufficient depth, even under the worst conditions in places like Nevada, Arizona, even Alabama, Georgia. So to modulate the cooling output, we talked about the bypass. There are other ways to modulate the output. One is to split it into rows. And so you can have 8-inch deep media that's sort of row split in that it's basically 2 4-inch, and you can have one 4-inch section that's 50 to 70% effectiveness. The problem with row split is that even then you get most of the cooling with just the first couple inches. And so you can still have issues with overshooting. So we're not big fans of row split. Phase split basically means break it up into sections sort of side by side, right? And so if you had a section and you cut it in half, and so so water could drip on one half and not on the other half, you would get half the cooling effectiveness. The problem there is similar to what I talked about with the bypasses. How do you make sure that the supplier temperature coming out of your air handling system is well mixed? So phase split can give you some real challenges on mixing your supplier. The bypass we've talked about, as you throttle the flow rate through the bypass, you can get more air through the media as a way to hold a supplier temperature set point. Again, similar concerns with mixed air coming out of the well-mixed supplier. You can use phase and bypass, basically put a damper in front of the media as well to force more air through the bypass. The issue there is you're going to need to have your bypass full side. So you need more sort of surface area or area in your air handling system, which can be a challenge. Pulse control. So on that data center, we talked about the fatal flaw, what we ended up doing is instead of dripping water continuously over the media, we just dripped it in enough volume to basically like a chill water valve. We modulated the water flow to get the supplier temperature. The issue there, of course, is that it scales up the media. The media is designed to basically be fully wetted. So you're usually running 3 to 4 times as much water over the media as you're evaporating so that it's always wet, kind of like a cooling tower. If you're just dribbling water, you get scale on the media. And so it basically plugs up the media pretty quickly. And so it ends up requiring that media to be changed out frequently. Another option that we have seen used is you can actually put the media in the outside airstream, not in the mixed airstream. Typically like a cooling coil or a DX coil, you'll put the media in the mixed airstream. If you put it in the outside airstream, you can get perfect temperature control because basically you use your outside and return air dampers to modulate the flow rate through the media. You can't use it for humidification then in the winter because now you could be bringing 0-degree air through your media. As I've argued, it's not important to use it for humidification. The big downside of this option is that it uses actually a lot more water. Timer a break now. I'm going to set my timer for another 5 minutes and then we'll pick it back up then. So let's get into some of the details of air economizing with direct evap cooling. So here's some of the basics. And we've seen some fairly complicated designs, and we think it can be really boiled down to something pretty simple. We typically run all air handlers at a common speed to maintain the cold aisle, hot aisle DP, right? We talked about that. So the air handlers are on some master control sent to all of them in terms of fan speed, but then each one controls individually for supply air temperature. So you'll control each economizer to a economizer supplier set point. We'll use, say, 65 degrees. And that economizer control loop will first open the outside air damper to 100% before shutting the return damper. Probably what you've seen on a lot of equipment is that the outside air and return damper operate sort of opposite each other. So that it's a 50-50, each damper is 50% open. If you use this fully opening one before shutting the other, then it half and half, both dampers are 100% open. And so it's just sort of a trick, or a trick, if you will, for reducing fan energy, right? Reducing the pressure drop and getting the same result with less fan energy. Scheme we've used not just on data centers, but on everything. We'll have a high supply air relative humidity loop that may reset the economizer maximum. And so what that will do is that if 65-degree supply air is going to result in supply air more than 80% relative humidity, changing my pointer so it doesn't disappear. What will happen is that the economizer will say, you can't open the outside air 100%, or you can't shut the return air 100% because you're going to be too humid at 65. And so it'll basically sort of naturally drift up. And so it may supply 67, 68, and that naturally brings down the humidity. So that's the economizer. So this air handler here is showing outside air damper here, the return damper coming from above. And so that's how we would how we modulate those economizer dampers. And then the direct evap will have a separate supply air temperature set point. So we might be controlling the economizer to 65. We might not turn on the direct evap until our supplier gets to 80. So there could be a period of many hours during the day where the outside air temperatures stay 67, 70 degrees. And we'll just be supplying 100% outside air. But when it gets all the way up to 80, then we'll turn on our direct evap, and we'll have a PID loop that's going to modulate. It's going to modulate the bypass damper opposite the DDC loop. And the damper will start at 0% open when the loop is at 100, actually sort of the other way around. When the loop is at 0, the bypass will be fully open. So we'll be mostly bypassing and only using a little bit of air through the media. And then as that isn't cool enough, we'll slowly shut the bypass, force more air through the media. And we'll have stages of spray turned on and off at different conditions. And so this air handler shows a bank of media here and a bank of media here. These banks were actually split in half. So we had 4 stages, if you will, of direct evap. And those are staged on when the loop gets above a certain amount for a certain amount of time. You stage on the next stage. And when the loop gets down low, you're over cooling. You're going to be opening the bypass and then eventually shutting off the stage. So that's how the stages are turned on and off. And the temperature is sort of controlled. This is perfect. The supplier won't always be exactly 80 degrees. It might go down to 78 up to 82, but that's okay, right? The data center doesn't need exactly 80 degrees. The other important thing with a air economizing system is you need to have some way to control your exhaust. That's usually off of a space pressure PID loop that first modulates the exhaust damper open and then modulates the exhaust fan speed. We aren't showing the exhaust as part of this air handler because it wasn't. The exhaust fan can be separate from the air handler. But you need some way to measure the space pressure and then modulate your damper. Often you can just open the damper and not even turn on the fan. But when you're bringing in lots of outside air, then eventually you'll need to modulate the fan as well. Some important things not to do with air economizing and direct evap is you don't want to shut or throttle the economizer when the direct evap is operated recently, at least when you're operating it for cooling. If you're operating it for humidification, that's a little different. But what can happen if you're trying to do cooling is that if you overshoot and say you start to shut your economizer, there's still moisture in that media. And what can happen is you can basically build up the humidity level in the space. And so whenever you're on direct evap for cooling, you want it to be a one-stir system. You want to be on 100% outside air. You don't need to use the outside air temperature or the outside air humidity in the sequences. You don't really care what the outside air conditions are when you're doing direct evap. All you care about is what's being supplied into the space, because that's going to dictate how you control your dampers and control your media. So you don't even need to know what the outside air temperature and humidity. All you need to know is what the supply air temperature is. And so again, it's a pretty simple system at the end of the day. You also don't need to use any kind of discrete modes of operation. We've seen people try to do very complicated sequences that say when the outside air is in this region, temperature and humidity, you do this and you do that. This sequence works regardless of whatever the outside air conditions are. And like I said, you don't even need to know what they are. So we use the same sequence, summer and winter, and keep it simple, right? KISS principle. There's a waterside to direct evap, right? You need to keep water flowing over the media when you want it to be operating. So here's a simple schematic of a sump. It's common to have one sump per air handler. You can also have a sort of remote gang sump that serves all the air handler, but this would be a schematic for one air handler, right? You've got a sump here. That's this sort of green box. You have a float valve to fill up the sump. And then the sump has a pump, and the pump basically pumps water up through valves that control the flow rate to different sections of the media, right? We like to do base split. So we'll break the media up into different sections and flow water over different sections, depending on how much cooling we need. And the water just kind of goes around in a circle here, right? Some of it gets evaporated. Most of it just comes back down and gets pumped back up. You'll need some sort of conductivity control, just like a cooling tower. You need to have the ability to drain out some of that water because the conductivity will get too high, right? The concentration of solids in the water gets too high. So you need to do conductivity control. Because it's water that's being evaporated into the airstream, you can't chemically treat it typically. And one way to do treatment to mitigate biological growth is with UV filtration. So that's very common in data centers is to use UV. And typically in the winter, when you're not using the evap, we'll shut off the flow so this can't be filled up, and then we'll just drain it out so it's dry. So a lot of the year, this sump is dry. When your air handler when your deck PID loop starts to call for cooling, then we'll fill up the sump, turn on the pump, open the valve, and get the flow. So back to how do you modulate direct evap? This is a design from another engineer's drawings of a direct evap system where they had split the media into 4 stages of different sizes, right? This one was 10% of the total area, 20, 30, 40. And then it came up with this sequence here. As your PID loop output increases, the first step was to start with just this 10% stage. The next step was to turn off the 10% and turn on the 20% stage, then turn on the 30, 40, etc. And this before even starting to modulate the bypass damper. This was the bypass damper was the last part of their hidden loop mapping. We found that didn't work very well. And the reason is that the media can take 15 minutes to get wet and even longer to dry out. And if you turn off this stage and turn on this stage, you're really going to have both of them operating quite a long period of time. And so it's you're sort of fooling yourself into thinking you can get that fine of a control because it takes a long time to turn on and turn off. Kind of like steering a super tanker, oil tanker. Turn the wheel, but it might take a long time before it actually starts turning. Okay. So what we found in our experience is to have stages of equal size instead of 4 stages of different sizes. We'll basically split it into just 2 or 3 equally sized stage. And then once you bring on a stage, you kind of keep it on because it takes a long time to get going and a long time to stop. So you basically just sort of stack them on top of each other. So we would have control valve 1 turn on, then we would turn on valve 2, then we would turn on valve 3. And as I said, we would modulate the bypass throughout. And that sort of gives you the modulating control that you really don't get with the step control of the individual stages. I think I'm going to pass this slide. This was a way to illustrate the difference between outside air and mixed air. And suffice it to say, you can put it in either location, but putting it in the outside air uses more water. Okay, so we've talked about air economizing with direct evap, very similar concept with chill water. One difference is that now you do care about outside air conditions because you're typically going to have an economizer high limit switch that you're going to use to switch from free cooling to full mechanical, or from partial free cooling, integrated free cooling to full mechanical. And so now you do need to know if your return air is hotter than your outside air, you want to shut off your economizer. One word of advice there is never use enthalpy as a way to control an economizer. It's actually not even allowed by code in California anymore. And the main reason is that enthalpy sensors or humidity sensors are hard to calibrate and often get bad information. Whereas dry bulb is generally much easier to accurately measure and therefore not do the wrong thing in terms of enabling or disabling your economizer. So we only use dry bulb to enable and disable economizer. Summarizing air economizers, they generally improve reliability and certainly improve energy efficiency. An air economizer is pretty much the most efficient way to cool data center, even compared to liquid cooling, I would argue. But there are risks. There's a risk of infiltration and pressurization issues. I talked about the data center that we worked on that had a lot of dust that was literally causing equipment failures. And those issues can persist even when the economizer is disabled. Because you have such large outside air and exhaust air dampers, it's hard to keep the data center even tightly sealed when the economizer is disabled. So maintaining pressurization is sort of the solution there. Even when the economizer is disabled, sometimes you'll need to have a means of pressurizing the data center. Exhaust recirculation, we talked about that with the package units. It can be a tricky thing. With data centers, you're bringing massive massive amounts of air, and configuring your intakes and exhausts to keep them from recirculating is non-trivial. Certainly can be done, but as the data centers get bigger and bigger, it gets harder sometimes. Snow intake. Data centers are going to be in places where it snows, and we've seen real issues with snow being sucked into the outside air intakes and then basically becoming water in your system, right? Getting your filters wet, sucking through your mechanical system. Coil freezing, you need freeze protection. You need to think about how you're going to avoid that. One curious issue that we saw, we didn't expect, is that one data center was trying to use barometric relief only for economizer relief, and that meant really big dampers. And those dampers were so tall that there was actually a stack effect where the hot exhaust air was going out the top of the damper at the same time that cold air was being drawn in at the bottom of the damper. So the space was positively pressurized, but we were still getting infiltration through the damper. And stratification of supply air, again, organizing and orienting your dampers is really key. These can all be mitigated. And basically here's sort of how to do that. So one of the things we've seen is to basically be conservative on the relief fan total static pressure. It doesn't cost you much to design your relief fan for 1 inch of external static compared to 1/2 inch or 1/4 inch. Be conservative on makeup unit sizing. So if you're using chill water or some other system where you're going to be shutting off your economizer, as I said, you can have infiltration issues. And so you need to have some sort of way to keep the space pressurized even when your economizer is off. Use modulating dampers and relief fans. We've seen data centers where they try to use stages, and stages just simply don't give you good control. So you want to make sure you have fully analog control. Redundant, elevated, shielded outdoor air references. It can be hard to get a good outdoor air temperature. And if you have an economizer high limit switch, you want to make sure you're looking at the right temperature. Rolling average, based ambient pressure signal. So sometimes if it's windy, you can have a hard time getting an accurate pressure signal of the space to the ambient. And so what we use is, especially doors open, things like that, you can actually have a fairly noisy signal. And so what we do is use a rolling average. It might be like a 2-minute rolling average. So it's sampling base pressure every, say, 10 seconds, and then averaging those signals over a 2-minute period to tell you, okay, here's a smoothed out, less noisy signal of what you really are controlling, what your real pressure is. And that's a better way to modulate your relief and make sure your space is positively pressurized. Multiple outside air sections with separate analog output. So that deals with things like snow intake, stratified supply air, even this relief damper stack effect issue can be addressed by having the ability to control separate sections. You're going to have an outside air damper that's going to be sized for 100% of the air, but in the winter, you only want a tiny amount of outside air, typically because it's so cold that you mix your 0-degree outside air with 100-degree return air. You're mostly return air to get your, say, 75-degree supply air. And you'll get better mixing by basically forcing all the outside air through one small section. And that can help you with stratification of supply air, coil freezing, etc. Okay, another type of economizer, if you will, is indirect evaporative cooling. or another type of evaporative cooling is to use indirect rather than directed outside air. So instead of humidifying the outside air directly, you can humidify outside air that's passing through a heat exchanger, and that will cool down the air passing through the other side of the heat exchanger. So this is sort of a schematic of an indirect unit that we worked on a data center. It's basically just recirculating return air through this heat exchanger. And then, as I said, the heat exchanger has on an outside air side that's pulling outside air. It's spraying water over the heat exchanger. And so basically that can cool the outside air or cool the recirculated air down. And then to supplement that, there's a DX coil that provides additional if the heat exchanger can't do the full thing. And the big advantage here is that we're not bringing in any outside air. So we don't have to deal as much with particulates and filtration and space pressurization because it's basically a sealed space. Another picture of that same unit, sort of showing a little bit more what that heat exchanger looks like. There's these spray nozzles that spray water on the outside of these tubes. And then the recirculated air goes through the tubes on one side, and on the other side, there's heat transfer through the cooled surface with the spray on it. Some interesting features about iDeck performance. This graph is showing the wet bulb depression effect. So how effective that heat exchanger is as a function of the airflow rate. What's the recirculated flow rate? And it's also showing the pressure drop. And so the pressure drop goes down very quickly as the flow rate goes down. And the effectiveness also goes up as the pressure drop goes down. With data centers, you almost always have redundant units and you're often not at full load. So it's very common to be operating at, say, 20, 30% flow per air handler. And then you're operating a very low pressure drop through your heat exchanger, a very high effectiveness. So the system efficiency gets really good at part. Similarly, the flow rate through the scavenger fan, which is sort of the outside air side of the heat exchanger, pressure drop is going to go down with the flow, how much you speed up and slow down that scavenger fan. And slowing down the scavenger fan, you still get a lot of good heat transfer, wet bulb depression effectiveness, even at very low speed on the scavenger fan. So the efficiency stays pretty good or gets even arguably gets really more efficient because you get such a low pressure drop, such low fan energy, and you're still getting a lot of effect. So it's a system that has very good park load performance. And at peak, it has the advantage of typically being able to size the DX for less than the full capacity. So this was in North Carolina. We were able to size the DX only for 38% of the peak load. If we were using an direct air economizer DX, we would probably have to size the DX for 100% when the economizer couldn't provide the cooling. But with this indirect evap, we can get away with what we call trim DX, or only partial DX capacity. It's still actually a fairly expensive system, even though you aren't necessarily sizing the DX for 100%, because there's a lot of material involved in that heat exchanger, right? So that's not trivial. Here's a sequence that we used. I don't think I'll get into the details there, but basically we have a supplier loop that we use to stage. There's a damper on the scavenger because even without the spray and without the scavenger fan, you can get overcooling just from stack effect through that heat exchanger. So sometimes you have to basically block off the heat exchanger, But once the heat exchanger is fully open, then you turn on the scavenger fan. At some point, you'll turn on the spray so you can get sort of dry cooling before you turn on the spray. Then once you've got your spray on, your scavenger fan running at full speed, if that's still not enough cooling, then you start to work your DX, right? And if you have big stages, you'll enable a stage at some point, have a disable at some point to minimize cycling of the stages. Real quick, another technology out there is the Lysenko cycle used by the Colorado product. I don't know a whole lot about it. It's similar to an indirect evap cooler, but instead of working off of the wet bulb condition, it works off of the dew point condition. So it has the potential to provide even more free cooling without DX. And so you could get away with even less DX trim. Of course, you need to balance that against the cost of this equipment. Pretty. Okay. I think that covers my section for a while. Brandon, you take it over.
Okay. Most of the systems that Jeff has been talking about use a flooded aisle design, where we essentially have very large air handling systems that then distribute air down cold aisle to multiple servers. There's another common strategy in data centers and in rack labs, which we'll call distributed airtight cooling. And these often make sense in multi-level facilities or other locations where you just quite literally don't have either the roof space or the space on the side of the building to plug in a bunch of air handlers. And the two we'll touch on are in-row coolers, which Jeff already mentioned a little bit earlier, and then active and passive rear doors. In the past, we had a couple other options on these slides, but have since removed them since these are kind of the two dominant distributed strategies that you'll run into in data centers these days. Here's an example of IRC. I think Jeff actually had something very similar to this earlier. Essentially, the next slide, what we're doing is taking air that dumped into the hot aisle by the server rack and then pulling it back out with the IRC, and the IRC has a chilled water coil or a DX coil in it that then cools the air down and distributes it back into the cold aisle. And the image on the left, essentially what you're seeing is an installation where the IRCs have been plopped into the white space before the servers have been installed. In this case, we have chilled water IRCs with the valve train overhead. The other common strategy is something called a rear door, which there are two options. One is a passive and the other is an active. We'll start with passive rear door, and it's called a passive rear door because it relies on the fans that are integral to the servers to move airflow across the rear door coil. So we're looking at a rack. The air is coming in again from the cold aisle side. The rack is pulling the air through, and then it's pushing it through the heat exchanger, which lives on the back side of the server cabin. So the air effectively comes back out of the rack again at the cold aisle temperature. The cooling medium can be either chilled water or condenser water, depending upon the application and what your design ambient conditions are, as well as the supply air temperature or the cold aisle temperature that you need for your application. When a coil is out of service with this design, effectively that just means that the load is spread across the remaining rear doors within the data hall. So there's built-in redundancy. Typically, we've seen this strategy be effective at up to 20 kW per rack. Anytime you go above that, you tend to get in the territory where a active rear door approach makes more sense. One of the key things with rear door is you need to make sure you have dew point control within the data center. And I'll pull about that in a second, and then I'll explain why that's necessary. And perhaps this should be obvious, but maybe not, is you need to seal the rack. If there are opportunities for airflow to bypass the heat exchanger and dump into the white space, well, that's problematic because you need all the air going through that heat exchanger so it gets cooled down to the cold aisle condition. So this is an open-ended, right? And so when you're getting to those loads that are above...
Brandon, you have a question?
Yeah.
Sorry, Brandon. Yeah, I was about to ask, like, what do you see the type of equipment that are used specifically for these type of dehumidification processes?
A lot of times it'll be a small custom single zone air handler that has its own dedicated direct evaporative system. So unless you had a really large, ginormous data center that did have substantial dehumidification loads, you, I guess, could consider having a small dedicated chilled water plant that was cooling to a lower temperature and supplying all of the dehumidification air handlers if there were many. But in most cases, because it's a small load, we typically see just a separate DX system.
What's the magnitude of these dehumidification loads that we are talking about
I
here?
mean, it varies
Like,
based on the size of the facility, but we're talking less than 5% of the design. Hopefully that helps.
Okay, thank you.
Okay, so if we're getting above 20 kW per rack, a strategy that's using either IRC or passive rear doors is kind of getting to the edge of its utility. As an example, a large IRC, we've done some custom IRCs that are roughly have about 44 kW capacity, which is pretty high for an IRC. So you might be in a situation then where you have 2 racks and then an IRC and then 2 racks and IRC. A lot of space within your data hall gets eaten up with IRCs. And that, when we're getting to that density, switching to an active rear door makes more sense. And an active rear door is different than a passive rear door because it has integral fans. And so we're no longer relying on the fans that are within the server racks themselves to move air across the rear door. And so the way this is controlled is you'll have a differential pressure sensor across the rear door assembly. If you see where my cursor is here, you have a DP across this, and the fans will modulate to maintain that DP to be effectively zero, right? Because what happens when the fans turn off? Well, if the fans are off, then the differential pressure between the servers and the coil starts to build up. And so as the airflow across the servers increases, that DP builds up, and the PID loop responds by increasing the server fan speed to maintain effectively zero DP across this assembly, which means the door flow is matching the rack flow. And so these can go up to fairly high densities. Here we know up to 75 kW per rack. No different than a passive rear door. You still require dew point control within the data center. So what are some of the hydronic options for serving these distributed air side systems? But in contrast to some of the options that Jeff was going over, it's not like we can tie an air side economizer onto an IRC, but we still want some form of economization to operate the data center more efficiently. So we typically might have a chilled water plant that has an integrated waterside economizer, or in some climates, we might just have strictly what we'll call a condenser water plant, because we can get cool enough water using strictly economizing throughout the entirety of the year that we don't need chillers. And in other cases, we will have a waterside economizer system that then has what we call trim chiller capacity, because that means that, say, on a design day, we can do 50% of the load still with the economizer. Then we can do the other 50% with the chillers, and the chillers don't need to be sized for the full load data center. So here's an example of a pretty plain vanilla chilled water plant. We haven't yet added the complication of a waterside economizer to this design. What you're seeing is 3 chillers in parallel. We have a primary only distribution configuration, meaning we have a single set of pumps that is sending water through both the chillers as well as out to the distribution system. This is the data center. We can imagine it's a small one that only requires N+1 redundancy. So 2 of these chillers require design load. The other one is redundant. The same thing is likely to be the case for both the chilled water pumps and the condenser water pumps. And we'd probably be doing exactly the same thing with the cooling towers as well. The next system option is what we'll call a waterside economizer only system. So we basically have deleted the chillers entirely here. And what you're seeing is that we have an open condenser water loop that's flowing through the cooling towers. And then we isolate the distribution that's going to the white space to serve IRC, their rear doors, via heat exchangers. And The basic control scheme here is that we modulate the flow through these heat exchangers on the tower side to maintain a target supply water temperature that's going out to the loads. And then the pumps on the secondary side that's serving the load are controlled to maintain some differential pressure to ensure that the valves at IRC, the rear doors, or what have you, are able to get their required flow. And then what we typically do in most of our installations, because there are a lot of climates where we can't do just this waterside economizer only option, but they're pretty much any climate we're going to operate in. We don't want to just do chiller only because that's going to be very inefficient for a lot of the year. So we'll meld the concepts together and do something like this, which is a waterside economizer system with trim chillers. This looks actually a lot like the previous slide, but what we've added to the system is a set of chillers that are downstream of the waterside economizer in the chill water loop. So the basic idea is that the chill water return comes back from the load. It first flows through the waterside economizer heat exchangers to do as much cooling as possible. And then only the remaining trim load is handled by the water-cooled chillers, which again are in series with those heat exchangers. All right, some other options. Water usage is becoming a more and more important consideration in data center design. And so we see a lot of owners going for strategies that minimize water usage. In a lot of cases, it's also just a means of simplifying things. So we see a lot of colo facilities where instead of having a water-cooled chilled water plant, they'll instead have an air-cooled chilled water plant. And one way to eke out some additional efficiency from that design is to use an integrated dry cooler. So a dry cooler is less efficient than a waterside economizer, a traditional waterside economizer, because what you're approaching is different. With a traditional waterside economizer, we're able to approach the ambient wet bulb. With a dry cooler, we're approaching the ambient dry bulb. But obviously in the middle of the winter, there's still going to be a lot of hours in most climates where that ambient dry bulb is plenty low to do effective cooling without needing to use a refrigeration. So on the screen now are a couple of different examples of this system. I think all of the major manufacturers in the market offer some flavor of an air-cooled chiller with an integrated dry cooler. The one on the left corresponds to the schematic on the top right. And the way this system is configured essentially is that the dry cooler coils are, let me add a pointer so I can sketch out here for a second. So these dry cooler coils shown down here, they essentially live directly on the outside of the condenser. So what's happening then is that ambient air is first flowing through the dry cooler free coil, and that's where the chilled water return is also starting, right? So say the ambient temperature is, 50 degrees outside, and we have chilled water return at 80 degrees. Well, we get some free cooling off of this, and then that air goes through the condenser coil. So we're able to use the same set of fans that are integral to the condenser system also for this free cooling coil. So there's some economy there in terms of components because we're specifying fewer fans to do this. One potential downside with this system design, however, is that because we're using the same set of fans, this set of fans has to do two things. One, it's trying to provide as much free cooling as possible, but it also needs to maintain efficient head pressure in the refrigeration circuit. Head pressure is effectively the difference between the saturated condensing pressure on the condenser side of things and the saturated suction temperature on the evaporator side of things. Most chiller systems, particularly those that use oil, need a minimum amount of pressure differential in order to properly operate. So what you can see with some of these systems is conditions where these fans will actually slow down to maintain minimum head pressure. And in doing so, they reduce the amount of free cooling that they're providing. So there's a trade-off of using this integrated condenser and free cooling design. Another approach that some other manufacturers take is to separate the free cooler out into its own bank of coils that's independent from the coils that are used for the condenser. And this allows us to, for instance, run these coil fans as hard as we want to provide as much free cooling as we can without consideration for that head pressure control constraint. The downside, however, is that now the system has gotten a little bit bigger because it takes up a larger footprint. All right. One thing to consider is whether you even should be providing standalone dry coolers or taking advantage of the fact that manufacturers do offer this product, whether you have a dry cooler integrated to your air-cooled chiller. From an efficiency perspective, there can be major benefits to actually providing separate dry coolers. So on the left is an example of an integrated dry cooler. On the right is a standalone dry cooler. And I think the critical consideration here, and these are examples of primary secondary system, is where the dry cooler is connected relative to the decoupler. If this were a primary only system, the same consideration would apply, but it'd be where the dry cooler is connected relative to the minimum flow bypass. Because once you get below minimum flow in a primary only system, which can be fairly high for air-cooled chillers, you effectively run into the same constraint that you would for a primary secondary system with a constant speed primary pumps. So the issue here is that in these integrated systems, there's a risk that you're diluting the return water temperature that's going into the dry cooler. So we can imagine a scenario where the primary flow is exceeding the secondary flow. So we have some flow going out chilled water supply. We have some of the flow that's coming this way through the decoupler, and then it's getting blended back with the chilled water return. And when that happens, the chilled water return temperature that the dry cooler sees is higher than the temperature coming back from the load. And the lower you have the temperature going into the dry cooler, the less or the smaller percentage of the load in an integrated condition that the dry cooler can do, meaning you're doing more of the cooling using your chiller. That issue is eliminated entirely if you have a separate dry cooler, because the temperature coming back at the dry cooler sees is the actual chilled water return temperature from the load. And it's only after the dry cooler that you're taking any of the flow that's going through the decoupler and blending it with the return. So it's an important consideration, and one where we did an analysis for a small system for an owner a couple of years ago. And our annualized energy calc suggested that the system with an integrated dry cooler, so the option from the manufacturer, had roughly on the order of, believe this or not, 2 times the annual energy use of the option with a separate dry cooler. And the answer here is going to vary significantly based on your system. But the reason that this was true in our case was that the systems under consideration had very high primary flows. So this was a primary only system, but very high minimum flows in a primary only system. So it meant that we had a lot of hours where we were diluting the return temperature going to the loads. And the return temperatures coming back from the loads were very high in the system. So they were 90 degrees. And there were a huge free cooling opportunity that we were essentially wrecking by blending in chilled water supply at 60 degrees with 90 degrees coming back from the load. This slide is provided just to demonstrate that when you are selecting air-cooled chillers with integrated dry coolers, you need to do your homework on how their efficiency varies with ambient dry bulb temperatures. So these are 3 different options from 3 vendors. And we can see that each of these was selected for some design condition, but a couple of them clearly do not provide nearly as much economizer cooling at middling OA temperatures, so between 50 and say 60 Fahrenheit, as the other does. You hear that a couple are still operating at on the order of 4 kW per ton, when the other one is dropping all the way down, at least theoretically, to less than 0.1 to 0.2 kW per ton under those similar conditions. And then here's another option that adds just a little bit more complexity to the system concept, where we're putting an evaporative pre-cooling coil upstream of the dry coil. And so what this is doing is it's allowing us to not fully approach wet bulb the way we would with a true waterside economizer, but it's depressing the dry bulb temperature of the ambient air that's hitting the economizer coil, and in doing so, increasing the amount of economizer hours that we get out of the system. There are a couple of benefits to this. One is obviously the energy efficiency benefit of that, right? You're increasing the amount of free cooling hours you have, which is great. But there's also potentially a first cost benefit. That's perhaps not intuitive because you're adding more components to the system, but you are significantly decreasing electrical load and at design. And that's because even under design condition, when you perhaps can't do any free cooling, what you are doing is reducing the entering air temperature that the condenser coil sees. And by doing so, you're reducing the lift across the chiller, and that increases chiller efficiency, which in turn reduces electrical load. So it allows your electrical engineer to potentially size systems more aggressively than they would have with just a standard air-cooled chiller. So in this example, we've sized these systems and seen a 30% reduction in peak electrical load. The downside of this sort of system is that it adds obviously a lot more complexity, because now we have makeup water that we're needing to provide to all of the adiabatic cooling pads that we wouldn't have had otherwise. And we also are adding a reliability risk, because now the system relies on water under design conditions to make sure that the chillers can provide their design capacity. This next slide, it didn't have a really good home, so it's kind of a standalone one-off, but I did want to touch briefly on the concept of a modular data center. Jeff showed this earlier, but it's more or less a data center in a box, and basically an air hammer that wraps around a set of servers. So that could be anywhere from 5 to 20 servers in a single row that are going down the middle of this thing. And the MDC, or the modular data center, will include both the racks, the cooling, the electrical, and the controls infrastructure. These systems are commonly direct evaporatively cooled, but you can also get them with DX systems or served by a chilled water plant. And from an owner's perspective, one of the nice things about these systems is that they are commoditized. They can streamline the commissioning process. There is an example of data center that Jeff and I worked on, or a couple of them, maybe back in 2016 and 17 at this point, where we commissioned 6 or 7 of these things per site. And certainly the first 1 or 2, we found a number of issues, but after the first couple, the amount of rework or commissioning time was reduced substantially, because we're dealing with a commodity that's just repeated over and over again. All right. This is probably actually a good break point. We could squeeze another 4 minutes out of the class and start talking about liquid cooled servers, but I think we'll stop now and start off on Wednesday with this as a clay flight and a new topic. If there are any last questions, I think we can, I'm happy to take them now before we sign off. Take that as a no. Thanks, everybody.
Brandon, there's a question here in the chat. What's the most common heating system, if any, for large server rooms? We're located in Midwest, North, and high elevations where temps are often below 30 for extended time. So what's the most common heating system for server rooms?
I would say still no heating system for large data centers. Usually there's enough load, even if it's freezing outside, that say you had a system that had an airside economizer, you would just be trimming the amount of outside air that you're bringing in and using a large fraction of recirculated return air to meet the load. Jeff, you have anything to add to that one?
No, well, maybe one thing. We worked on data centers where the data center is built out before the computers show up. And so sometimes we will put in temporary electric heaters, but basically, as Brennan said, once you get any load in your data center, you'll never. Okay, I think covers it for today. Pick it up on Wednesday.